Okay, thank you very much. And first of all, I would like to thank you, Martinas, and all the ISC staff and also speakers and so on for the wonderful opportunity to speak here. We have lost some, so we are starting a little bit later, so I'll try to be brief and fit into the 25 minutes to give some time for questions. And actually, we are starting with this graphic on the that you can see on my presentation. It is depicting a theme that is recurring in the let's say in orbit servicing and debris removal area, and so the moment of capture of the let's say satellite being a subject to servicing or some operations. And this is the main theme. I will talk about some specific robotic solutions that are, let's say, important enablers to achieve some of those capabilities. And I believe those are also topics that, let's say, fit well with the sustainability theme of this year ISC. So I will go now to the agenda of this presentation. Well, I will give you a brief introduction to the GAP space as a company, as you might not know it very well. Some short examples of our general, let's say, robotic portfolio and past projects, not necessarily only in orbit servicing area. And then I will go into some specific projects and products that are directly related to the servicing and debris removal and end-of-life operations, and also life extension of the satellites. So yes, going to the let's say general information about GAP space, we are the let's say spin-off company of the PIAP, which is an industrial institute for automation and robotics in Poland. We are now a separate company focused mostly on space activities, and in general there are two main area focus for us, two legs on which we stand basically. One is the space robotics, and the other one is mechanical ground support equipment. So yeah, those are the two main areas of operation. Going forward with the robotic systems, as I mentioned, what we are aiming for is to provide solutions or enablers that can serve in a variety of servicing roles and the orbiting, and that includes most notably robotic arms or manipulators, but also end effectors, and including more specifically a LAR gripper, so a gripper designed to grasp the launch adapter ring of a satellite, and also a multi-purpose gripper for, let's say, general purpose servicing operations. And that team of LAR, which might well, LAR gripper might sound like a very specific thing, but actually LARs are widely recognized like as a common element that let's say multiple or almost all relevant spacecrafts have. So they are identified as a common interface basically. And that allows for grasping or attaching ourselves to the client satellite. And there are also other accessories, most important sensors, and especially force-stroke sensors, which are very important for the space robotics, as they are crucial in, say, compliant robotics, in adaptive operations where the robotic arms and end effectors are interacting with free floating bodies, and also some vision systems capabilities, which are also crucial, especially in the very last phases of, let's say, rendezvous or grasping operations, where the distances between spacecrafts can be are low. So those are the main product areas in the robotics section. As for MGSC, we have experience with integration stands, adapters, clamp bands, hoisting and lifting devices, and also other types. I will not go into too much detail in this area. However, please free to contact us if you're interested. Now, going briefly to the our space robotics portfolio of completed projects, I will now talk a little bit about mobile robots and rovers. Those are also an important aspect of our work in robotics, and here we will have just a brief look on some of the examples of such projects. For example, Racer here was an ESA study aimed to characterize the maximum realistically achievable speed of a moon rover, which also involved a lot of preparation in terms of representing the relevant lunar environment. And also in going further with mobile robotics, we were also involved in Paraspera European Commission PROACT project, which aimed at demonstration the cooperation capabilities between multiple robots. And in that project, we were designing the mobile platform with a robotic arm and also some end effectors. So that was the important step in gaining experience with robotic arms on our side. Yes, so going forward, there are also some build to print projects. For example, here Chablis characterization breadboard for locomotion of sample fetch rover is also a part of our previous experience. We can see this model here during test campaign on inclined type. And last but not least, there is also a part of our previous experience with end effectors and grippers. And so here in the theme of grasping the launch adapter rings, in the middle here we can see the ADREX grippers, which were our, let's say, first steps in that area. And those were intended to grasp a particular type of LAR. So it was designed specific to a certain mission, a certain type of satellite. And now, since then, we are also moving forward in terms of providing more, say, general solution, and the end effectors that are actually quite universal and can grasp let's say, variety of types of LAR, and I will touch more upon this subject later. So going to the currently developed projects, I will start with Titan. Titan is an ESA project. It's about the robotic arm development for on-orbit servicing operations, and PIAP Space is the prime contractor and integrator of the arm, and is leading industrial consortium composed of Polish companies, including the Center for Space Studies of Polish Academy of Sciences, which is responsible for a control algorithm design and some of the electronics. Also SpaceIF, which is responsible for analysis, most importantly thermal analysis within that project. So robotic arm is, of course, a very, let's say, universal and adaptive feature that can serve in a variety of roles. I will go now into the more specific information. So within the Titan project, the goal of this project is to reach TRL6 by the end of this year for the whole arm, and the arm is visualized here on slide. It is characterized by the range of around 2 meters. It can have a weight of 50 to 70 kilograms depending on configuration, and it has some let's say important distinguishing characteristics. First of all, it is self-lifting, which is kind of rare for the orbital robotic arms. So it can operate to a limited degree in 1G environment on Earth, which also simplifies validation testing. It has also a lot of redundancy, built-in redundancy. So it's 7 degrees of freedom arm, and that allows us to operate even with loss of one of the joints. At least partially. It has redundant databases, power lines, and sensors, including most importantly the four-stroke sensor, which we'll touch briefly upon later. So the project is currently at the joint level. So we have an engineering model of the joints. We are going forward throughout this year with the model of the whole arm. Now, as part of the Titan project, there is, let's say, reference mission designed, and that because it's the whole aim of the project is to develop an arm, so there is no specific mission related that would be, let's say, a source of our requirements. So we have an reference mission that let's say includes some of the common aspects that we could expect in the real missions, and one of those real missions we will also discuss a little bit. So basically this close proximity operations and extending the arm, grasping the launch adapter ring of the other satellite. So here on the diagram, the gray the gray block represents the client or the satellite under servicing, and the blue one is a servicing satellite. So so we are grasping the launch adapter ring of target satellite and positioning ourselves at some reference position. And from this point, various things can happen. We can have missions where, for example, the rigid connection between spacecrafts is established that way, or then the robotic arm can transfer, let's say, this connection into a separate clamping mechanism, then free itself and do some servicing operations. Also, we can have scenarios with two robotic arms where one of them is responsible for grasping and the other one is responsible for manipulating objects, and so on. Now, going through the specific mission I talked to you about, we have a family of projects called EROS, and with a growing, let's say, complexity and technology readiness level from EROS to EROS Plus and the EROS IOD. At this point in time, we are actually at the border between EROS Plus and EROS IOD. And EROS stands for European Robotics Orbital Support Services. And the aim of the project is to demonstrate in orbit demonstration mission the ability to grasp a client satellite, to establish a connection, to perform servicing in form of exchanging orbital replaceable unit. So that represents a capability to install some kind of additional module into the client satellite, which could be used, for example, not only for servicing, but also as, say, life extension option. For example, we could attach a module that would provide an additional boost and increase in orbit and so on. And throughout the projects in EROS, we reached TR4. Now EROS Plus, we just ended with the demonstrations in laboratory conditions, and we are estimating TRL6 at this point in time. Now until 2025, the EROS IOD will be the next phase, which will hopefully be then proceeded by the actual mission with launch in the second half of 2026. So within that program, we are responsible for providing a gripper to grasp launch adapter rings, and also some dedicated interfaces, which I will show you in a minute. And the gripper itself is, as I mentioned, characterized by the fact that it is capable of grasping multiple types of launch adapter rings. It's not designed, it's not limited to one type only, as it was the case in the previous designs. It is characterized by, let's say, a very low mass for its capabilities of almost exactly 5 kilograms. And it has a large grasping envelope. So the grasping envelope is the, let's say, area or rather a volume of space in which we can let's say compensate, or the gripper has the ability to adapt itself to the movement of the LAR, because let's say real life is messy and we have a limited accuracies in all of the elements of the system. So it's always the possibility of there will be always some relative movement between two spacecrafts during these critical last phases of operation during capture. So we are quite adaptive in that area. Also, at the moment, with the EROS in EROS projects, we are cooperating extensively with other companies. So most importantly, the integrator of the spacecrafts, both client and servicer, because the in-orbit demonstration mission will carry its own client and then separate and then try to attach with him again on the low of orbit. The integrator is Thales Alenia Space France, and also we are cooperating with Germany's DLR, which is an integrator of the robotic subsystem, and that includes the DLR Caesar arm, which is also a space manipulator, and our gripper, and also interfaces, for example, standard interface hotdog, which is provided by Space Application Services, or CROM, which is provided by CENER. So there is really a multitude of companies, multitude of interfaces and solutions involved. We are also cooperating with GMV, with SINTEF, and now in EROS IOD, the consortium will grow to include even more companies. Now, going forward, we can see here some photos from the demo that happened at the beginning of this year. So in principle, we are training for two scenarios, as when dealing with the capture, we can have actually 4 scenarios in total. The most, let's say, easy one is when the client satellite is both cooperative and prepared. So it behaves nicely, it doesn't try to escape, and it also has some features that actually enable grasping, and that also help with the visual navigation, for example, some kind of markers. Now we can also have a cooperative but unprepared client. So that one is not trying to escape, but it doesn't have any specifically designed features that would help with the operation. And also we can have, of course, both unprepared and uncooperative cases. So in Eros Plus, we are dealing with cooperative cases in both unprepared and prepared variants. In unprepared,
Arcadius, your sound went off.
Prepared dedicated grasping interface, and that one has the advantage because the final point, the final position after the grasping is finished, is predetermined. So we have a predefined point of connection. During grasping LAR, that's not the case. We can grasp at any point around its circumference. So yes, going further, there is also an internal Polish project that is funded by the National Center for the development and for research and development. It's called Orbita, and its aim is to develop also a building blocks for the space robotic subsystems, and that includes a multi-purpose gripper, which is a modular design with here the lower with its lower elements being actually a full rotational module, which enables a 360-degree unlimited rotation. That is not the feature that robotic arms usually have, and it could be important, for example, in screwing applications, in attaching panels, in attaching connectors, harnesses, and so on. And also an effector that is attached on top of that, that has an ability to grasp different tools and also can detect what type of tool it is actually holding at the moment. And that could be used to a variety of functions, including, as I mentioned, exchange of some kind of exchangeable units, attaching connectors, grasping, let's say, general shape objects, pushing the solar panels that didn't open, and multitude other use cases. Now, let's say another building block important in this area is force torque sensor. So 6-axis force and torque sensors, which is a mechanical structure with strain gauges, but also it has an embedded electronics. So it is a module, it is a building block, a device in itself of mass of around 1 kilogram that can be attached, most importantly, at the end of the robotic arm, between the arm and its end effector, and it provides this essential force and torque feedback information to the control system of the robotic arm. And this is a sensor that we are developing in PIAP space in cooperation with German's Systeme, manufacturer of industrial sensors. Last mention, we are also, last but not least, we are also developing our vision system that is designed to help with that unprepared scenario. So it is capable of detecting the shape of the LAR and let's say guiding the systems in order guiding the other systems in this last phase. It is not something used in the Eros Plus project, but it is our own development for the future. And with that, say here we have current technology readiness of each of those subsystems for the nearest future, for this year. And the EROS IOD will be, as I mentioned, we have a planned launch date in 2026. So hopefully, we will see those systems in action. And here my contact information and also the contact information for the business development manager at our company. Please feel free to contact us.